Hi students, if you're watching this video, it's because you've already watched the atomic number video, and I told you to tune in for the next one, which is now going to discuss when we have different mass numbers for atoms of the same element and why. So in this particular video, we'll be talking about isotopes and explaining how elements or atoms of elements can have different masses. So I'm going to go ahead and share my screen. And walk you through this PowerPoint. And hopefully this will help. So, isotopes and the average atomic mass. So, we've already talked about how basically the atomic number, the number of protons, determines the identity of an element. So, magnesium, if you look at a periodic table, is in the 12th position of the periodic table. So, that number in that box in the elemental symbol, the smaller number is 12. And we notice that all of these atoms of magnesium have 12 protons in the nucleus. The other thing that all of these atoms of magnesium have in common is they have 12 electrons outside of the nucleus. That's because a positive 12 and a negative 12 make these atoms neutral. What is different with all of these isotopes of magnesium, so what is different with all of these atoms of magnesium is they have a different number of neutrons. And we can see that because if you remember that larger number, right, which we were saying was the mass number, the reason why it's the mass number, it was the number, it's equal to the number of protons and the number of neutrons, which are found in the nucleus, and those are both roughly 1 AMU. So we see that all of these are magnesium because they have 12 protons and 12 electrons, but how they differ is they have a different number of, or a different mass number, different number of neutrons. So isotopes, basically, we know that it's the proton that determines the element. So it's possible for atoms of the same element to actually have different masses due to having different number of neutrons. So when we're defining isotopes, remember when we learned the scientific theory, right? There's the what, right? There's the what and the why, right? And the what was our law and the why is our theory. So if we're talking about what an isotope is, that's easy. An isotope is atoms of the same element that have different masses. This is the what. The why is they have different number of neutrons. Now they can have different neutrons because it's not the neutron that identifies the element. Remember, it's the proton that identifies what the element is, but they can have different masses as a result. So isotopes are atoms with the same number of protons but different number of neutrons. The different types and amounts of each isotope is determined by nature, right? So there's a way to write what's referred to as a nuclide symbol that shows the number of neutrons and the variation, and we use the mass number. So this is an example of a nuclide symbol. You have the elemental symbol, and then you have the mass number, which is the number of protons and neutrons, on the top. I just tell students it's the bigger number. They put the larger number on top. And then the smaller number, the Z, is the atomic number, and that's always a number of protons. Because again, both neutrons and protons are 1 AMU, so the smaller number is just the number of protons, and that's how the element is defined. So all of these isotopes of neon, they're all neon because they have 10 protons. So again, the number of isotopes is determined by nature. And we see when we're looking at it, in this example, lithium has 2, carbon has 3, oxygen has 3, sulfur has 4. And then we can take those averages and we can come up with what you actually see on the periodic table as an average atomic mass. Now, the average atomic mass typically is not an integer. So you might be thinking, well, wait a second, why is it on the periodic table? If I look at magnesium in that 12th position on the periodic table, it's 24.31. It might say, 24.305. I'm just rounding to the hundredths place, and that's okay to make things simple. So someone might wonder, well, why? Why is it 24.305? If I was to look at, if I took an average of 24 plus 25 plus 26, and I divided it by 3, wouldn't that be 25? Well, it would be if you were doing what's referred to as an arithmetic mean. Arithmetic mean is where you just average all of the values or sum up all the values and divide by the number of values. But what we have to realize when we look at isotopes, the isotopes of the elements come in different percentages. So that's referred to as a relative abundance. So in nature, we don't have equal amounts of magnesium 24. We don't have equal amounts of magnesium 25 or 26. So you don't get an arithmetic mean. And we see that because we know that 24 plus 25 plus 26 divided by 3 would be 25, not 24.305. So this video shows us how to calculate weighted averages based on frequency. It makes a lot more sense when we look at it in terms of this. If a larger percentage is magnesium 24, shouldn't the weighted average be influenced more by the more abundant, the more frequent isotope? Yes, it's weighted more heavily. So we see it's obvious of the 3 isotopes, because the weighted average, the average atomic mass of magnesium is closest to 24, that 24, the isotope magnesium 24, should be the most abundant. So it's not a whole number. That average is, again, a weighted average. So because the masses of these elements are not the same and they're weighted, we need to calculate this average that's weighted. So how do we do a weighted average calculation? We basically take the mass of each isotope, and then we're going to multiply it by their percent. But remember, percents, so I can make any percent. I could say, let's say something is 50%. From basic math, we can convert percents to fractions very easily. 50% is just 50 over 100. So we're actually going to convert percents either to fractions. Now, if you don't like a fraction, that's totally okay. The other thing you can do is change it to a decimal. So you can just say 0.50. Now, why 0.50? Because this is the hundredths place, and 50% is 50 hundredths, right? And you can do this with any percent, right? If I had, 92%, that's just 92 over 100, right? And to make it a decimal, really all I'm doing is, because I'm dividing by 100, I'm moving this decimal over 1, 2, 0.92. That way, if I get a percent that's not a perfect ones place, like if I get a percent that's 37.34%, I can still easily change this to a decimal by just moving this over 1, 2, and the decimal becomes 0.3734. So now that I know how to convert percents to fractions and decimals, how do I calculate? The average atomic mass is basically going to be whatever that fraction or decimal for that isotope is times its mass, plus whatever that fraction for isotope 2's relative abundance is times its mass, plus the fraction of isotope 3, and so on, depending on the number of isotopes. So sometimes there's only 2. You wouldn't have to do this third one. Sometimes there's 4. You'll have to do it 4 times. But rather than just talk about it, let's do a calculation. So natural occurring chlorine we talked about earlier had 2 isotopes. It had chlorine 35, and we saw that it had chlorine 37. Why was that? Well, chlorine 35 had 18 neutrons, and chlorine 37 had the 20 neutrons. They're both chlorine because they both had 17 protons. But now we want to figure out what that average atomic mass, but we have to recall that it's a weighted average. So how do we do that? We're going to change these percents to decimals. So that's easy. We're going to move the decimal over 1, 2, 1, 2, and then we're going to multiply that decimal by their masses. So here's the solution. Convert to decimal form, multiply by mass. So chlorine 37. Oh, the slide went out of order. I'm sorry. So that would be this isotope right here, right? Chlorine 37. We changed that to a decimal, and the mass for chlorine 37 was 36.97. So we multiply the abundance in decimal form by the mass, and we get a certain amount. I call it the contribution to the overall mass. And then we go to chlorine 35, which we saw the abundance was 75.77 with a mass of 34.97. We convert the percentage to a decimal, and we get, by moving this over twice, 0.7577 times 34.97, and we get the mass contribution for that particular isotope. So to get the weighted average, we just add these two, and we get that it's 35.45. So we can see that on a periodic table. Again, the smaller number is what? The atomic number. And the atomic number is the number of protons. But on a periodic table, unlike nuclide symbols, which give you a mass number, which is the number of protons and neutrons, what a periodic table actually gives you is a weighted average of the isotopes and their relative abundance. So I hope this video helps in you seeing and understanding why that second number on a periodic table is not an integer. It's because it's a weighted average of our isotopes. I hope it helps you in calculating if you have the relative abundance of each isotope and the mass, which you'll be doing in your homework. And I'll show you in the next video how we can do problems that are a little bit trickier, that involve a little bit of algebra. So go ahead and practice this, apply this to some of the homework problems, and in the next video, we'll do a little bit of a trickier example. So thanks for watching, and let me know if you have any questions.